Ladies and gentlemen, good morning. My name is Hsin Ho Liu. Today, the article I'm going to review is from the last year Nature Materials. And the topic is the strategies for advancing cancer nanomedicine. As we know, the nanoparticle for cancer treatment has been used for years. But right now, the cancer nanomedicine so far can only minimize the toxicity. The efficacy is still very disappointing. How? As we in the average, the efficacy is limited by the physiological barrier posed by the tumor microenvironment itself. So in this paper, the authors try to discuss how to overcome these barriers posed by the tumor microenvironment. So in today's presentation, I will divide it into three parts. The first part is the background knowledge of the nanomedicine, and the second part is the main part. We'll discuss about the strategies for the cancer nanomedicine, and then finally the conclusions. The background knowledge of the nanomedicine comes from the 1986. Two independent studies in 1986 identified the mechanism for selective delivery for macromolecules to the tumor. The first paper is from Dr. Leonard Jarosky. He proposed that the tumor vessels are more permeable than normal vessels. And the second paper, the second theory is from the Yasuhiro Matsumura sensei. He reported that the tumor retains large molecules because of the poor clearance. So combine these two phenomena, it becomes the background knowledge of the nanomedicine. It means the enhanced permeability and the retention effect. We also call it EPR effect. So this picture demonstrates the EPR effect more in detail. As you can see, these are the normal tissue and these are the cancer tissue. So the blood vessels of the normal tissue are very tight. There is almost no hole inside the blood vessel wall. So when the drug, like a large molecule drug or a small molecule drug, going through the bloodstream, it's very difficult to penetrate the vessel wall. And only the small molecule can use the convection or diffusion effect to transport the small molecule to the cell. But inside the tumor tissue, as you can see, the blood vessel of the tumor is very weak. It has a large hole inside the vessel wall. And if because leak of the lamina propria and the endothelial cell, the blood vessel is very leaky. If the macromolecular drug, the size of the macromolecule is small than the cutoff size of the pole, it can extravasate into the interstitial space. And when it penetrates into the interstitial space, it has another potential to retain because the interstitial pressure is very high and the lack of the lymphatic drainage. So these two, enhanced permeability plus the increasing retention, makes the EPR effect. It can provide the selective delivery properties that can reduce toxicity in normal tissues. As you can see, the drugs to the cancer cell can only through this kind of mechanism, but in the normal tissue, there is no drug inside it. So this provides the selective delivery properties. So this EPR effect is the key pharmacokinetics feature of the nanomedicine. So we use this background. We can further divide to develop the strategy for the advancing nanomedicine. The first one is tailoring the materials to the specific tumor. This means how to design your nanoparticle to the best, make the best design. As we know, the tumor microenvironment vary very widely, and the cancer care is now undergoing a bioinformatics revolution. So everyone is every cancer is personalized therapy. The target therapy also tailored to each patient. But right now, the nanomedicine is still going on the one-size-fits-all approach. So we need to make better design according to the specific physiology properties of each tumor can achieve the better outcome of the nanoparticle. So this picture demonstrates how this drug can achieve the cancer cell. This green one is the cancer cell, and this blue one is the drug. So as you can see, the drug need to first transvascular penetration, and then later doing the interstitial distribution. So the boundary between the cancer cell and the drug are many layers, including the basement membrane, pericyte, endothelial cell, extracellular matrix, stroma cell. Then you can finally attach the cancer cell. So it's basically a very long way to reach the cancer cell. This picture demonstrates the more detail about the transport barrier. The first one, as you can see, the red dot is the nanoparticle, and the black one is the vessel. So the permeability of the tumor vessel is especially non-uniform. Not every vessel can extravasate the nanoparticle, and the nanoparticle extravasate only from some region of the vessel. And when they extravasate, they only penetrate a few cell layers into the tumor. And in the middle picture, you can see the green one is the nanoparticle, and the red one is the matrix. So basically, the nanoparticle is trapped inside the matrix. The matrix can block the nanoparticle through the hydrodynamic or electrostatic interaction. So the drug is difficult to penetration into the interstitial space. And the third one is according to the blood vessel. This green one is the vessel, and the blue one is the matrix. So only a few vessels inside matrix can be seen. As low as 20% of blood vessel in the tumor can carry blood flow. So these three mechanisms makes the distance a drug must travel to reach cancer cell up to hundreds of micrometers. This means a very long way for a drug to reach its target. So when we design the nanoparticle, we need to first consideration is the pore cutoff site. As the slide showed before, the site on the vessel wall is big enough to let the particle penetrate. So this definition is the largest particle can penetrate from the blood across the vessel wall and into the tissue. This will determine how rapid the nanoparticle will penetrate into the tumors, and that means the particular permits selectivity. So when we design the nanoparticle, we need to make how large the nanoparticle need to be. So we need to consider several things. One is each tumor, it has its own range, and the exact pore size is different in every tumor and every tumor site. So we need to make a critical consideration about the pore size heterogeneity. So make different consideration to each tumor can make the better. And besides the pore size, we need to consider another thing, is the matching the cancer to the particle type. So there are three aspects we need to manage about the particle type. First is the particle size, second is the particle shape, and the third one is the particle charge. According to the size of the nanoparticles, as we know, tumor penetration, intratumor distribution, and the plasma clearance, these all size dependent. So the nanoparticle size cannot be big enough, can't be too big, and it cannot be too small either. So if the nanoparticle is more than 11 nanometers, it will be eliminated by renal and the hepatobiliary clearance. Basically, they will destroy in the kidney and the liver. But if the nanoparticle is more than 11 nanometers, it will be cleared by the MPS system. So basically, in the average, the small nanoparticle has some properties. First, they will penetrate more rapidly and uniformly. Thus, they can reach more target cell, and they can carry more drug and more effective against the tumor. So So in the conclusion, the smaller nanoparticles can generally accumulate to a higher concentration in the tumor cell. So when we choose the size, we need to make the balance between the maximizing the tumor penetration, but while maximizing the tumor penetration, we still need to minimize the toxicity to the normal tissue and minimizing the clearance by the MPS. So average, and so in the conclusion, the smaller nanoparticles down to 12 nanometers appear to be the ideal for the cancer nanomedicine. This is the size. And the second aspect is the shape. Now we know the non-spherical nanoparticles penetrate tumor more rapidly because they have the shortest dimension of the nanoparticles. This shortest dimension makes them more clear more easily to be clear by renal filtration. But if the nanoparticle is large in their longest dimension, they will be cleared by the MPS unless they are flexible. So this is another consideration when we do the nanoparticle design. So according to the shape dependence of nanoparticle delivered, we need to turn in the shortest dimension for a balance between the maximizing the penetration and minimize the renal clearance, and also modulating the longest dimension to minimize clearance through the MPS. So right now, not a conclusion, but early principal studies indicated that a great deal to promise of the non-spherical nanoparticles for the best one. And then the third aspect is the charge dependence. The charge dependence is basically the surface chemistry modulation. So the ketonic nanoparticle can do more penetration, and the neutral and the anionic nanoparticle can do more distribution because the cell membrane is anionic. So the canonical nanoparticles can have the attractive electrostatic forces to the cell membrane, so they can penetrate more. But the neutral and the anionic nanoparticles, they don't have that kind, so they will more effective to binding to the matrix molecules. Another is you can decorate some surface antigen like the poly or other antigen to minimize the MPS clearance. This also included in the charge dependence consideration. So the third one is mostly innovative nanomedicine design. It means how to make the perfect nanoparticle. And then the second strategy is how to target the tumor microenvironment. Besides you got a good nanoparticle, you still need a strategy to target the tumor microenvironment. So the targeted tumor microenvironment in this aspect means the active targeting. The previous mentioned the EPR effect is the passive targeting, and this is active targeting. So we use the ligand, the ligand. The ligand is the bounded for the tumor receptor, so they have the affinity to go together. So use this phenomenon, you can promote the cell-specific recognition and the binding. So in this picture, as you can see, this is the drug, and it has large ligand on its surface. It can bind into the cancer cell through the receptor. So this is the better way to find the cancer cell. So active targeting is going beyond the passive EPR effect, so we need to use this phenomenon. But even we have the active targeting approach, we still have some challenging between it. Mainly the basically is the binding site barrier. What is the binding site barrier? As we said before, the drug needs to going a long distance to approach the cancer cell. But during the approach, the first cell, the nanoparticle encountered is not always the cancer cell. So how to avoid this condition is to overcome the binding site barrier. We have some suggestion in this paper. First, you need to balance the distribution and the binding rate, and use what kind of method? You use the fast diffusion nanoparticle combined with the low affinity ligand receptor pair, and this can make the better balance. And further, you can target the spatial receptor more than the normal receptor. This receptor is unique mutant or truncated receptor. this kind of receptor is almost cancer related. So you target the true cancer cell, and it can make better outcome. And besides the receptor, you also need to consider the type of the tumor. If your type is cellular tumor, you need to target the cancer cell itself. If the tumor is desmoplastic tumor, means the tumor is rich of the stroma cell, so you need to target the stroma cell first, and it will improve the retention rate. And besides the tumor cell, you also can target the blood vessel cell. If you target the blood vessel cell, it can make the vascular disruption and make the nanoparticle more easily to translate into the tissue. Another is target the tumor stroma cell, like the fibroblast or other immune cell. Because this kind of cell, they have the homogeneous receptor more than the cancer cell, so they can be improved in drug retention. So we need, in this aspect, we need to test a different kind of a ligand and a receptor combination to make the best nanoparticle. And we can also use the tumor microenvironment. As we know, the tumor microenvironment is also is more acid and more hypoxic. So if you detect the pH value or the oxygen saturation, you can differentiate the cancer cell from the normal cell. We can use this to do some smart active drug targeting with the kinetics that moderate with this characteristic. So this can become a new mechanism for trigger drug release, especially in the tumor microenvironment. So this control picture gives an overview of the clinical most relevant drug targeting strategy. The first one is the free drug. It's only through the penetration into the interstitial. But the EPR effect can make the retention rate increase and the permeability rate increase. But if you add the ligand, it can target the cancer cell more easily. And you can also use the tumor microenvironment to facilitate the targeting. These are all the most relevant strategy used right now. And besides the front two strategies, the last strategy is normalize the microenvironment. We know that each barrier to the drug delivery results from the pathophysiology change of the tumor. So the important thing is how to repair or how to normalize these abnormalities. So this strategy is more attractive because this can overcome the nanoparticle design alone. And we have three kinds of normalization. First is vascular normalization, and the second is stress normalization, and finally the metric normalization. The vascular normalization basically is to correct the excessive angiographic signaling. And in frankly speaking, you need to repair your blood vessel, make your vessel more mature and more homogeneous and less leaky. And through this, it will reduce the interstitial fluid pressure and increase the perfusion. And the second is stress normalization. The stress normalization is to reduce the physical forces inside the tumor. And we can target the collagen or other matrix molecules and make the matrix degradation or inhibition the fibroblast to reduce the solid stress. In this picture, as you can see, before treatment, there are lots of matrix or stroma cell here, and after treatment, there is no stroma here, only the cancer cell. So the interstitial stress is decreased. And the third one is matrix normalization. The target is matrix, so you need to degradation the matrix, modifying the matrix, or reducing the matrix production. So in this cartoon picture, you can see this is cancer cell and this is the stroma cell, but the extracellular matrix between them are disappeared, like the neck structure. So after the matrix normalization, it will improve the blood flow through the tumor. So finally, the conclusion. The cancer nanomedicine, as a consequence of reliance on the EBR effect before, is not insufficient to overcome barrier in tumor right now. So we need another strategies. So first, you need to make the better nanoparticle to especially tailored to the character of the tumor through the advanced targeting mechanism or the special tumor selective drug release kinetics. And besides the nanoparticle design and the tumor microenvironment targeting, you also need to balance the microenvironment through the normalizing approach, manipulate the tumor microenvironment. So this is today's article. Thank you very much.
Thank you. Very good presentation, but the time is too long. I will announce again. The time for each speaker is 7 minutes, so probably 10 slides will be enough for service presentation. Anyway, any questions or comments? Yes, please.
Thank you for the information. I want to ask, is the medicine is already in use now?
Right now, the nanomedicine, the FDA approved only 3 kinds of nanomedicine. Yeah, it is being used right now.
Okay, thank you.
I have a question about, you say this drug is through the penetration mechanism, but for those people who have bad diet habits or they don't exercise, they have their vessel with very few flexibility. So will it have any influence on this kind of job?
Right now, the ordinary physical property of the tumor vessel, like a diabetes tumor or hypertension patient, is not included in this kind of study. They only discuss with the cancer patient and the non-cancer patient. But inside the non-cancer patient, they don't determine any difference between a healthy vessel or a non-healthy vessel.
Okay, thank you.
More questions? Yes.
The design of the particle is the different sizes for each permeability or like tumor penetration. But how do you determine the tumor penetration?
The size differs very differently between different kind of cancer, like the cellular cancer and the desmoplastic cancer. They have different kind of cut-off hole size. So this need to experiment to test. So need to test the combination of the particle size and the shape and the charge, because even the same size, if you have different kind of shape or surface antigen, they will change the penetration rate.
Okay, any more comments? Okay, any questions or comments from Japan?
Any questions?
Thank you for your presentation regarding nanomedicine. Actually, the size and permeability have the effect on penetration of drug molecules. Sometimes high penetration can affect the normal cell. For this why you made conclusion to design antibodies for targeted cell. But I would like to know what is your prediction how the nanomedicine can be tailored for the targeted tumor cell.
Can you repeat your question again?
So you made conclusion that we need to design nanomedicine or nanomolecules for targeted cell because high penetration can cause or affect the normal cells. But I would like to know how we can design or tailor for the targeted cell, targeted affected or tumor cell. How we can do this now?
You mean how to design better target nanoparticle?
Or targeted affected cell. Because sometimes high penetration of nanomolecules medicine can affect the normal cell.
How to target the cancer cell?
Yes.
Basically, you can use two kinds of targeting. First is passive targeting, and the second is active targeting. Passive targeting is used the EPR effect because the tumor cell can retain the drug, the nanoparticle, because the EPR effect. So the normal cell won't have this kind of EPR effect. So this is passive targeting. And the second is another way is active targeting. Use the cancer cell speciality. Mostly the receptor on the tumor cell. We have the ligand to target to the receptor, and only cancer cell had that kind of receptor. So they have the affinity to combine together, and the normal cell won't combine with the drug.
Yes, understood. Thank you.
All right.
Thank you very much.